Let's look at a couple of problems where determining the torque from the weight of an object is important, and knowing that we need to locate the weight at the center of mass is crucial for solving it correctly. Here we've placed a meter stick on a fulcrum, and we've hung a half-kilogram mass on one side, and it's balanced by, well, we don't see anything, but we know it's the weight of the meter stick that is balancing the half-kilogram mass, and we want to figure out what the mass of the meter stick is. So a free body diagram of the meter stick. We draw the weight of the half-kilogram mass, and I'm calling it big M. And then the weight of the meter stick, I'm calling that little m, and that is placed right in the middle. And then there's a normal force from the fulcrum, but we are going to sum the torques about that point, and so the normal force won't have a torque and won't show up in our equations. And we need to figure out what the lever arms are. So we're told that the half-kilogram mass is at the 97 centimeter mark, and the fulcrum is at 85 centimeters, so this would be 97 minus 85, or 12 centimeters, or 0.12 meters. And then the lever arm for the weight of the meter stick, sometimes this can be tricky to figure out. Here we know this is at 50, and we're told the fulcrum's at 85, so it's 35 centimeters, or 0.35 meters. So we're ready to sum the torques about the fulcrum, and so we have the known weight times its lever arm is giving me a positive torque counterclockwise, and the unknown weight of the meter stick times its lever arm is giving me a negative torque. And we solve for little m, and we get 0.17 kilograms. Let's take a look at a similar problem, but this one's tougher. Here we have a beam at an angle rather than being horizontal. And it is in static equilibrium. It's free to rotate about this hinge, but we've tied a cable to its end. The cable is horizontal. That makes this easier. A harder problem would have the cable at some angle. And we want to figure out the tension in the cable. So we don't wonder how to proceed. We know we need a free body diagram. We need to draw and label the forces. So I have tension, that's horizontal, and I have weight of the beam, which is in the middle, or I should draw it close to the middle. And then there are also some forces here at the hinge, or one force with an unknown magnitude and direction. I prefer to break it up into two components, and I do guess them both positive, but here we're just going to find the tension, so we sum the torques about that point, so the hinge forces won't show up in our torque equation. Now we need to figure out the perpendicular components of the tension when we're doing torque, and so that would be this component. And so that is opposite angle theta. If you imagine these are two parallel lines and the beam is a diagonal, if this is theta, that's theta, so this is theta over here. And down here is theta, and I want the perpendicular component of the weight. That is what gives me torque. And so this angle here is 90 minus theta, and so the perpendicular component is adjacent to theta or opposite 90 minus theta. You could do it either way. And so some of the torques are 0. And so the torque from tension would be T sine theta. It's this opposite component. And it is positive, trying to rotate counterclockwise. And then don't forget the lever arm times the length of the beam, which was given as 4 meters. And then the weight of the beam itself is a negative torque, trying to rotate clockwise, and it's either cosine theta, or you could have sine of 90 minus theta here. Either one is going to work. It's up to you on how you figure this out. But that is the key thing, is you should be able to figure this out yourself. And then don't forget the lever arm, which would be half the length of the beam because it's at the center of mass. Those torques add up to 0. We can put our numbers in then. 4 for the length of the beam and 2 for the lever arm of the weight of the beam, and we get 210 newtons.